Okay, we have a child starting from rest at the top of a 3-meter-long frictionless slide. We'll bring friction into the picture a little later. Slide is inclined at 25 degrees above the horizontal. How fast will the child be moving at the bottom of the slide? Now, we certainly could use kinematic equations, but let's practice energy. Now, energy. What force or forces are causing this child to accelerate, to start from rest and achieve another speed?
Acceleration of gravity.
Gravity. Only gravity. Now, there's a normal force acting on the child, but is the normal force causing the acceleration? No. So, that means our equation we derived yesterday, the change of potential energy plus the change of kinetic energy has to be 0. This equation is going to be true as long as only gravity acts on our object, in this case our kid, or only a spring acts on our object. There's no spring in this problem. It will not be true if friction acts on the object. Friction takes energy away from this potential and kinetic form, and it changes it to another form. The total energy still stays constant, but it's not in the form of potential and kinetic anymore, or at least not totally. But this problem, we have a frictionless slide, so this is going to be fine. Remember, we also wrote this as initials on one side and finals on the other. Whichever way you like it, use it. They're equivalent equations. Okay. So here's our slide. Inclined at 25 degrees. Here's our kid. The kid slides down the slide. We know there's a normal force acting on the kid. We know there's a force of gravity acting on the kid. And it's the component of gravity parallel to the incline that makes the kid accelerate. That's why the child is speeding up and going faster and faster. Bless you. Now, as far as energy is concerned, with energy, it doesn't matter if your acceleration is constant or not. We've already determined, come up with our equation that relates potential to kinetic energy. So we need to decide. So I'm going to put our initial point up here, because that's where the kid is starting. And I'm going to put the final point down here at the bottom of the slide where we want to know how fast the kid's moving. Where would you like to call y equals 0? Bottom? Sounds good to me. If y equals 0 at the bottom, what can you tell me about the potential energy of the kid at the bottom? 0. Exactly right. The gravitational potential energy is 0 wherever you decide to put y equals 0. You can put it wherever you want. It doesn't matter. You just have to be careful in terms of choosing your y and calling your, figuring out if your y is positive or negative. For example, if we had chosen y equals 0 at the top, we would need to put a negative value in for our y at the bottom. That's the difference. So initially, up here, there will be potential energy because the child is not at our chosen y equals 0. Kinetic energies. What can you tell me about the kinetic energy at the top? 0. The kid started at rest. You cannot have kinetic energy if you're not moving. Finally, at the bottom, the kid's going to be moving. We're looking at how fast he's moving. That's the question. So we know there's kinetic energy here at the bottom. Since there's no friction and drag isn't a factor, all of the potential and kinetic energy the child starts with, the child must maintain throughout his motion, and he must end with the same amount as well. So we can say the initial energy he has, the mgy initial, has to equal the final energy he has, the 1/2 mv squared. M's are gone. Bringing the 2 over. There's our equation. Really quick, easy way to get to our relationship between the speed and the height. Now, gravitational potential energy depends only on vertical height. That kid, whether the kid goes straight down, say the kid decides to jump off behind the ladder and get to the ground, versus going down the incline and get to the ground, they'll have the same speed. Doesn't matter how he gets there, because he has the same initial height. Okay? So the amount of potential energy he has is the same because he's at the same height. The amount of kinetic energy he has at the bottom is going to be the same as well. The difference will be the direction of his velocity vector. If you were to actually write out his velocity as a vector, he'll be heading at an angle that way. He would be heading straight down that way. So the direction is all that's different. But that doesn't matter. We're only looking at how fast. I didn't ask you what direction he was going in. So only how fast energy works quite nicely. But before we can solve this, we need to figure out his initial height. The problem tells us that the slide is 3 meters long. It's an angle of 25 degrees. So what is y initial? 3 meters. We're opposite the angle, so sine of 25 degrees is our initial height. I'll plug numbers in. 2, g is 9.8 meters per second squared. Y initial was 3 meters times the sine of 25 degrees. So that tells us how high the kid was initially. I get 4.98. So approximately 5 meters per second is how fast the kid will be traveling when he gets to the bottom of the slide. So energy works quite nicely to relate speed to height. It was a pretty quick little step getting our equation there. You do have to remember, though, gravitational potential energy, mgy, depends only on vertical distance, not at all on horizontal. Okay? And that's because if an object was moving on a horizontal surface, it's not gravity that's making it do so. It's got to be some other push or pull or friction, something along those lines. Gravity can only accelerate an object as it moves vertically. So that's why we only depend upon our y value.